What if the past is not truly gone? What if it isn't an intangible memory, a ghost that lives only in our minds, but a physical place you could witness right now with your own eyes? It's a tantalizing thought, the stuff of fiction. Yet it is the profound and literal reality of our cosmos. The universe in its unimaginable grandeur is a museum of its own history, and the price of admission is simply to look up. Every glimmer of light that graces your retina is a traveller from a bygone era, a messenger carrying a story from a time that no longer exists. For the closest stars, the message is only a few years old. For others, it began its journey when civilizations rose and fell on Earth. And for the most distant galaxies, that whisper of light embarked on its solitary pilgrimage through the cold, silent void before our planet had even fully formed. This is the fundamental truth of our existence, a consequence of the universe's most sacred, most inviolable law. Light, for all its brilliance, is not instantaneous. It has a speed, a cosmic speed limit. This constant, this unwavering velocity through the vacuum of space is the ultimate anchor of our physical reality. At nearly 300,000 kilometers per second, it is a speed so immense it beggars belief, a velocity that could circle our entire world more than 7 times in the blink of an eye. Yet on the scale of the cosmos, this incredible swiftness becomes a patient, almost glacial crawl. The distances between worlds, between suns, between the great spiral arms of galaxies are so profound, so mind-breakingly vast that even this ultimate speed is dwarfed into insignificance. It is this very limitation that transforms every telescope into a time machine. When you gaze upon the Andromeda Galaxy, our closest major galactic neighbour, you are not seeing it as it is today. You're witnessing it as it was 2.5 million years ago. The light from that majestic spiral of 1 trillion stars has been journeying across the intergalactic void for longer than our species Homo sapiens has walked the Earth. We see its ancient form, its past glory, a ghostly snapshot preserved in photons. We can never know what Andromeda looks like. Now. We can only wait for millennia upon millennia for newer, younger light to complete its epic voyage and deliver the next frame of the story. This principle is more than just a curious fact. It is the bedrock of modern cosmology, the very foundation upon which our entire understanding of the universe is built. The speed of light, designated by the letter c, is woven into the deepest mathematics of reality. It is the c in Einstein's iconic equation E-rem-c2, the immutable value that links energy and matter. It is the ultimate speed limit that nothing with mass can ever hope to reach, the cosmic barrier that separates cause from effect. This constant dictates the very flow of time, the shape of space, the dance of gravity. It is the metronome of causality, ensuring that an event in one part of the cosmos cannot instantly affect another. Without this universal speed limit, the orderly progression of time would dissolve into chaos. A star could explode and we would feel its gravitational ripple at the exact same moment we saw its light, with no warning, no delay. The universe would become a place of terrifying simultaneity, but it is not. There is a delay, there is a journey, and the duration of that journey we believed was as predictable, as certain as the laws of mathematics themselves. We use this predictability to measure the cosmos itself. We build our maps of the universe upon this foundation of light's constant, reliable travel time. By measuring the faint redshift of a distant galaxy, the subtle stretching of its light waves by the expansion of space, we can calculate its distance with astonishing precision. We know that a galaxy with a certain redshift is, for instance, 10 billion light-years away. This is not a guess. It is a calculation derived from the universe's own physical laws. It means the light we are capturing from that galaxy today began its journey 10 billion years ago, and we therefore know with absolute certainty that it must have travelled for 10 billion years to reach us. The distance and the travel time are two sides of the same coin, inextricably linked by the unyielding constant of c. Every observation, every calculation, every single theory about the origins and fate of our universe rests upon this one simple, beautiful, and supposedly unbreakable assumption. Light travels from point A to point B in a straight line at a constant speed, taking a precise, non-negotiable amount of time to do so. Nothing can speed it up. Nothing can give it a shortcut. For decades, this principle held firm against every challenge. It was the North Star of physics, a beacon of certainty in a cosmos filled with mystery. We pointed our most powerful instruments at the deepest, oldest corners of space, and the rule was never ever broken. The light from a supernova in a distant galaxy arrived exactly when our models of cosmic expansion said it would. The ancient radiation from the Big Bang itself, the cosmic microwave background, tells a story of a 13.8 billion year journey that aligns perfectly with our understanding. We built our entire cosmic narrative around this one unwavering truth. The story of the universe was a story written in light, and we were confident we knew how to read it. Until the day we received a message that arrived before it was sent. It began not with a bang, but with a quiet anomaly in a flood of data. Deep within the digital archives of the Atacama Large Millimeter Array, a sprawling network of 66 radio telescopes, perched high in the Chilean desert, a single object refused to conform. This wasn't a discovery born of a deliberate search for the impossible. It was an accident, a ghost in the machine that astronomers at first dismissed as an error, a glitch in the software or a flaw in one of the sensitive receivers. The target of their observation was a massive turbulent cloud of interstellar gas and dust. In our own Milky Way, a stellar nursery where new suns were being forged. They were charting the intricate magnetic fields that sculpt these cosmic clouds, hoping to better understand the violent and beautiful process of starbirth. Among the thousands of distant background light sources they used as reference points, one stood out. A quasar catalogued as J047+24556. A quasar is the ferociously bright nucleus of a young galaxy, powered by a supermassive black hole consuming unfathomable amounts of matter. They are the most luminous objects in the universe, celestial blowtorches visible from across billions of light years. Because of their immense distance and singular point-like nature, they are the perfect cosmic lighthouses. Astronomers use them as fixed points in the sky navigational beacons against which the subtle movements of closer objects can be measured. This particular quasar, J04372+22456, was well documented. Its distance had been measured and cross-referenced by multiple independent surveys using the most reliable techniques at our disposal. The verdict was unambiguous. Its light showed a redshift that placed it with very high confidence, approximately 6 billion light-years from Earth. 6 billion years. A journey that began when our own Sun and Earth were just coalescing from a spinning disk of primordial dust. The team in the Atacama was not studying the quasar itself, but rather the way its light was being subtly bent and distorted as it passed by a foreground star here in our galaxy. This phenomenon, known as gravitational microlensing, is a direct prediction of Einstein's theory of general relativity. Any object with mass a planet, a star a galaxy, warps the fabric of space-time around it. Light, which we once thought travelled in perfectly straight lines, must follow these curves. As a foreground star drifts across our line of sight to the distant quasar, its gravity acts like a lens, a cosmic magnifying glass. This lens doesn't just brighten the quasar's light, it also creates multiple distorted images of it. By observing the precise separation and timing of these images, astronomers can calculate the mass of the foreground star with incredible accuracy. It is a powerful and well-understood technique, a routine part of the modern astronomer's toolkit. In this case, the foreground star was an unremarkable red dwarf, one of countless trillions scattered throughout the Milky Way. Its path was predictable, its gravitational influence calculable. The team's models, built on a century of validated physics, made a very specific forecast. As the red dwarf passed in front of the quasar, it would split the quasar's light into two distinct pathways. One path would be slightly shorter, a more direct route to our telescopes. The other path would be bent more severely by the star's gravity, forcing it to travel a slightly longer distance. This meant the light from the two images would not arrive at Earth simultaneously. There would be a time delay. One image would appear, first followed moments, days, or even weeks later by the second, depending on the precise alignment and the mass of the lensing star. The computers churned through the equations of relativity, factoring in the star's mass, its velocity and its distance. The prediction was crystal clear: the time delay between the two images of quasar J037+456 should be approximately 2.5 months. The observation campaign began the giant dishes of the Atacama Array, staring unblinkingly at their target. everything proceeded exactly as expected. The first image of the lensed quasar flared into existence, its radio waves collected and recorded. The countdown began. The team waited for the second image to appear, the echo travelling along its longer, more curved path through space-time. They waited for 2.5 months, their instruments ready. But it never came. Weeks turned into months. Months stretched into a year, then 2, then 3. The second image remained stubbornly and possibly absent. The project was on the verge of being declared a failure. Another case of a miscalculation, or perhaps an unexpectedly complex gravitational environment. The data was shelved, the mystery filed away as an unsolved puzzle. It was only years later, when a graduate student was tasked with cleaning up the old data archive, that the truth was uncovered. The student, seeking to understand the original error, decided not to look forward from the first image but to look backward. On a hunch, they scanned the observational data from before. The first image was predicted to arrive, and there it was. The so-called second image, the one that was supposed to take the longer path, was already present in the data. It had not arrived 2.5 months late. It had arrived nearly 7 years early. The implications of this discovery sent a shockwave of disbelief and quiet panic through the astronomical community. It was a result so profoundly impossible, so utterly contradictory to the foundations of physics, that the initial reaction was to assume the student had made a catastrophic error. The data was reanalyzed by senior scientists, then by independent teams around the world. Every possible conventional explanation was exhaustively tested and systematically ruled out. Was the distance to the quasar wrong? No, it was confirmed by multiple other observatories. Was the mass of the foreground star miscalculated? No, the lensing data itself confirmed its mass. Was there some unknown cloud of dark matter creating a complex, unforeseen gravitational lens? Models were run for thousands of hours on supercomputers, but no configuration of matter known or unknown could reproduce this result. No physical model could account for a 7-year shortcut. Let us be perfectly clear about the magnitude of this paradox. For light to arrive 7 years early from a journey of 6 billion years, it would need to have travelled through a tunnel in space-time itself. It would mean that the distance between the quasar and Earth was somehow for this specific light shorter than the space it was travelling through. It is the equivalent of a marathon runner finishing the race an hour before they started, or a letter arriving in your mailbox the day before it was postmarked from across the country. It violates our most basic understanding of sequence of causality of the very fabric of time. The universe we have always known has a rigid set of rules. It has a speed limit. It has a one-way arrow of time. It has a geometry that, while curved and warped by gravity, is fundamentally coherent and predictable. The light from this one single star, this time travel star, suggested that somewhere somehow the rules had been broken. This observation is not just a curiosity, it is a profound crisis. It stands as a direct challenge to Albert Einstein's legacy and our entire century-old conception of gravity and space-time. It forces us to confront the possibility that the universe may contain structures or pathways we have never imagined, shortcuts that defy the known laws of physics. We are now faced with a stark and dizzying set of possibilities. Perhaps space-time is not the continuous smooth fabric we have always envisioned, but something far stranger, something that can be tunneled through or bypassed. Perhaps there are exotic forms of matter or energy that can create what physicists have only ever theorized about in the realm of science fiction, a stable, traversable wormhole. Or maybe the speed of light itself is not as constant as we have always believed. The existence of this impossible signal, this phantom echo from the deep past arriving ahead of schedule, has opened a door we never even knew was there. Behind it lies either a simple mundane explanation that has so far eluded the world's finest minds, or a revolution in physics that will rewrite our understanding of everything. We are adrift in a sea of new questions, each more unsettling than the last. What created this impossible shortcut through the cosmos? Is it a natural, though exceedingly rare phenomenon? Or is it a sign of something else entirely? The data is unambiguous. The calculations are verified. The impossible has happened. And now we are left with only the central, terrifying and exhilarating question that drives all of science: how How can light, the very measure of time and distance, possibly arrive early? It began not with a thunderclap, but with a whisper. A quiet flicker of data streaming from a robotic eye perched high in the thin cold air of the Chilean Andes. At 3:17 a.m, an automated alert buried amongst millions of routine celestial measurements flagged a subtle inconsistency. It was a digital shrug, a momentary glitch in the grand cosmic symphony that most systems would have dismissed as noise. But this system was different. It was programmed to hunt for the impossible. For Dr. Aris Thorne, asleep thousands of miles away, this single line of code was a summons. It was the first tremor of an earthquake that would threaten to shatter the very bedrock of physics, the beginning of the end of everything we thought we knew about time and the universe. For over a century, our understanding of the cosmos has been built upon a single immutable pillar, the speed of light. It is not merely a velocity, but a fundamental constant of nature, woven into the very fabric of space-time. At a blistering 792 kilometers per second in a vacuum, it is the universe's ultimate speed limit, a law more sacrosanct than gravity. Nothing we have proven time and again can travel faster. This cosmic speed limit, often simply called c, is the rigid spine of causality itself. It ensures that an effect can never precede its cause. It is the celestial governor that keeps the past, present and future in their proper inexorable sequence. Because of c, the universe makes sense. This universal constant gives us our grandest measuring stick, the light year. It's a term so common we often forget its profound implication. It isn't a measure of time, but the colossal distance that light, the fastest thing in existence, can travel in a single terrestrial year, nearly 10 trillion kilometers. When you use this celestial ruler, you're not just measuring space, you're peering deep into the past. The light from our own sun takes 8 minutes to reach your eyes. You're always seeing the sun as it was 8 minutes ago. The nearest star system, Alpha Centauri, is over 4 light years away. The faint glimmer you see from it tonight is a ghost, a photon postcard mailed 4 years in the past. And as we gaze deeper, our telescopes become time machines. The glorious Andromeda Galaxy, our closest major galactic neighbour, appears to us as it was 2.5 million years ago, when our own ancestors were first shaping tools on the plains of Africa. Every distant galaxy, every shimmering nebula is a temporal echo. The further we look, the deeper we plunge into cosmic history. We are seeing not just how the universe is, but how it was. The speed of light is the metronome of this cosmic clock, ticking with perfect, unwavering regularity. It dictates the age of everything we see. A galaxy 1 billion light years away cannot under any circumstances be seen as it was 900 million years ago. Its light simply could not have reached us yet. The travel time is fixed, absolute and non-negotiable. This is not a theory. It is the foundational grammar of our reality. This is the universe Dr. Elena Vance and her team at the Atacama Large Array had dedicated their lives to mapping. Their target was not a nearby star or a neighbouring galaxy, but something far more ancient and violent. They were chroniclers of the deep past, their gaze fixed upon an object designated SDSS J074 D-215. To the uninitiated, it's a meaningless string of characters. To an astronomer, it is the address of a monster. 0749 is a quasar, a blazing, ferocious heart of a galaxy, in its infancy located an almost unimaginable 6.3 billion light-years from Earth. We are seeing it today as it was when our own solar system was just beginning to coalesce from a spinning disk of dust and gas. A quasar is not a star. It is a supermassive black hole millions or even billions of times the mass of our Sun, actively feeding on its host galaxy. As stars, gas and dust are torn apart by its immense gravity, they form a swirling accretion disk, a cosmic maelstrom heated to trillions of degrees. This process unleashes a torrent of energy so luminous it can outshine its entire galaxy 1,000 times over. J0749 is a celestial blowtorch, a beacon burning across more than half the observable universe, a lighthouse from a bygone cosmic epoch. For Vance's team, however, its brilliance was secondary. They were interested in a peculiar quirk of its location. By a stunning celestial coincidence, the light from J0749 does not travel to us on a straight, unimpeded path. Its journey is warped by the presence of a massive galaxy cluster, a colossal congregation of dark matter, and thousands of galaxies that sits directly in its line of sight. This intervening cluster, a mere 3 billion light-years away, acts as a powerful gravitational lens. Just as Einstein predicted, its immense mass warps the fabric of space-time around it. Light from the distant quasar that passes near the cluster is bent, magnified, and split. Instead of seeing one image of J0749, our telescopes see multiple images of it smeared into arcs, and ghostly copies surrounding the foreground galaxy cluster. This phenomenon is more than just a cosmic curiosity, it is a physicist's dream. Each of these lensed images represents a different path the quasar's light has taken to reach us. Some paths are slightly shorter and more direct. Others are forced to take a longer, more circuitous route around the densest parts of the cluster. Because quasars are not static objects, they flicker and vary in brightness. Over time, we can watch for a specific flare-up in one lensed image and then wait with a stopwatch in hand for that same flare to appear in the others. The time delay between the arrival of these signals, which can be days, months, or even years, combined with our models of the lensing galaxy's mass, allows us to perform an extraordinary calculation. We can measure the exact physical length of each light path. We know precisely how far the light has travelled. And here lies the crux of the experiment. If you know the exact distance travelled, and you know the unwavering speed of light, you can predict the travel time with astonishing precision. It is a simple, fundamental equation: distance divided by speed equals time. For over a decade, Vance and her team had been doing just that. They meticulously monitored J0749, recording every subtle fluctuation in its lensed images. They built the most sophisticated models of the foreground cluster's gravitational field, refining their calculations with data from the world's most powerful telescopes. Their work was a masterclass in cosmic cartography, a painstaking effort to map a path across billions of light-years. They were not looking for anomalies. They were attempting to use the time delays to independently measure the expansion rate of the universe, a noble if conventional goal. They believed they were simply reinforcing the known laws of physics. They were wrong. The first hint of the puzzle came quietly in the sterile air-conditioned data rooms of their institute. A graduate student running a routine validation check on a newly processed dataset found a discrepancy. The time delay between the arrival of a light from image A and image C of the quasar was off. Not by much a tiny fraction of a percentage point against a journey of 6 billion years, but it was outside their meticulously calculated error bars. It was flagged as a probable software bug, a calibration error in one of the instruments, or perhaps an unaccounted-for pocket of dark matter in the lensing cluster. For 6 months, the team chased these mundane explanations. They rewrote their code from scratch. They recalibrated every sensor. They refined their mass models, adding layers of complexity that bordered on the baroque. But the anomaly refused to disappear. In fact, as they gathered more data, it grew stronger, more statistically significant, more defiant. The problem was not with the time delay itself. That was an observed fact. The problem was what it implied. The team had two known values: the precise physical distance the light had travelled for each path, and the precise time it took to travel that path. When they used these two bulletproof observationally confirmed numbers to calculate the speed of the light itself, the result was impossible. The numbers screamed that the photons travelling along the path that created image C had, for their entire 6.3 billion year journey, travelled consistently relentlessly faster than the speed of the light. It was a conclusion so heretical that no one dared speak it aloud at first. They simply stared at the figures on their screens, a cold dread mixing with a tantalizing, terrifying curiosity. The data was unequivocal. Across a journey spanning nearly 60 sextillion kilometres, the light from J0749 had arrived at our telescope 7 years ahead of schedule. 7 years. It was as if a marathon runner had not only won the race, but had arrived at the finish line a full day before the race even began. It was a complete violation of causality, a dagger pointed at the heart of Einstein's relativity. The universe, according to their data, was not behaving as it should. The cosmic metronome was broken. Dr. Vance felt the weight of a century of physics pressing down on her. Every instinct she possessed as a scientist screamed that she had made a mistake. An error so subtle yet so profound that it had eluded her entire team for years. For another year they kept their findings secret, poring over every last detail, inviting trusted colleagues to tear their analysis apart in confidence. They searched for any alternative explanation, no matter how exotic. Could some unknown form of matter be creating a gravitational shortcut, a wormhole-like tunnel through space-time? The models didn't support it. Could the light have been accelerated by some unknown interaction? Physics had no mechanism for such a thing. Every logical path, every rational explanation led to a dead end. They were left with only the raw, inexplicable data. The light was early. With trepidation, they submitted their paper to the most prestigious journal in astrophysics. It was titled, with deliberate understatement, An Anomalous Time Delay in the Lensed Quasar SDSS JSO 749-215. The response from the scientific community was immediate and brutal. It was met with a tidal wave of skepticism, a collective institutionalized disbelief. This is not a weakness of science, it is its greatest strength. The scientific method is a rigorous, unforgiving process of challenge and verification. Extraordinary claims require extraordinary evidence, and Vance's claim was the most extraordinary in a generation. Her team's work was put through a crucible of peer review, fiercer than any they had ever imagined. Reviewers from competing institutions demanded their raw data, their code, their calibration logs. Independent teams across the globe, using different telescopes and different software, reanalyzed the public archives of data on JSO 749. They were not trying to help. They were trying to find the fatal flaw to be the ones to debunk this outlandish result. For 2 years, the anomaly was attacked from every conceivable angle. Every line of code was scrutinized. Every assumption in their gravitational model was challenged. It was the scientific immune system at its most aggressive, attempting to identify and destroy a potential pathogen of misinformation. And then one by one, the confirmations began to trickle in. A team in Germany using a completely different modelling technique arrived at the same impossible conclusion. A group in Japan observing a new flare from the quasar confirmed the time delay to an even higher degree of precision. The anomaly was not a glitch. It was not an error. It was real. The firewall of doubt had held it, had tested the data with scorching fire, and the data had passed through the flames unburnt. The quiet whisper from the Andes had become a global roar. The paper was published, and the world of physics was plunged into a state of profound and unsettling crisis. The pillar was cracked, the sacrosanct law had been violated. We now stand before a mystery deeper than any we have faced before. We have an observation, a verified, confirmed, undeniable fact that simply cannot be true. A message from the deep past has arrived 7 years before it was supposed to. It is a letter delivered to our doorstep from a ship that, according to our maps, is still 7 years out to sea. This isn't just a puzzle, it's a paradox made real. And it forces us to ask a terrifying and exhilarating question. What if the rigid spine of causality isn't as rigid as we believed? What if the universe has a loophole? The signal was not a whisper, it was a thunderclap in a silent cathedral. And in the hallowed halls of science, the first reaction to thunder is not awe. It is suspicion. Before you can accept the sublime, you must first eliminate the mundane. So began the Great Inquest, a planet-wide methodical effort not to prove the impossible, but to find the simple, embarrassing mistake that would make it all go away. The first suspect, as always, was us. Human error. It's a comforting thought in a way. A misplaced decimal, a software bug, a misaligned mirror. These are mistakes we understand. They are human failings and they can be found and fixed. They do not require rewriting the laws that hold the universe together. The telescopes themselves were the first to be placed on trial. The array of orbital and terrestrial observatories that had captured the event, a network of glass and steel and silicon united in a single unblinking gaze, was subjected to a level of scrutiny that bordered on forensic. Engineering teams on 3 continents were mobilized. They didn't just review the current data, they resurrected archived logs digging back through years of calibration files, temperature readings and guidance corrections. Every captured photon from that supernova had a history, a chain of custody from the moment it struck a detector to the second it became a pixel on a screen. That entire chain was now a crime scene. Was it a timing glitch? A flaw in the atomic clocks that synchronized the global network independent labs were tasked with re-verifying the master time signals, comparing the GPS-linked timestamps against the most stable oscillators on Earth. They searched for a phantom lag, a hiccup in the planet's heartbeat. The clocks, however, were perfect. Down to the nanosecond, they held their rhythm unblemished and absolute. The problem was not in the when, perhaps it was in the what. The intricate charge-coupled devices the electronic eyes of the telescopes were interrogated. Could a rogue cosmic ray have struck a sensor at the exact right moment, creating a cascade of false signals that mimicked the signature of a supernova? Such events are known, they are planned for, and they are filtered out by sophisticated algorithms, so the teams went back to the raw, unfiltered data. They sifted through the digital noise, the blizzard of background radiation, an instrumental hum, looking for the ghost in the machine. They found nothing. The signal was too clean, too powerful, too texturally correct. It wasn't a glitch. It was a symphony with the precise spectral crescendo and decrescendo that marks the violent death of a blue supergiant. To fake it, a glitch would need to be a malevolent artist painting a masterpiece of astrophysical data by sheer random chance. The odds were less than 1 in a trillion. The software was next. Millions of lines of code, the invisible architecture that translates light into knowledge, were combed through by rival teams. One group's mission was to prove the code was sound, the other's was to break it. They hunted for rounding errors, for flawed assumptions buried in legacy subroutines, for any tiny crack in the logical edifice that could have let this impossibility through. They built simulations feeding the code with fake data of a correctly timed supernova, and it performed flawlessly. They then tried to imagine how a 7-year error could be introduced. The corrections for Earth's orbit, the subtle wobble of its axis, the general relativistic effects of the Sun's gravity, all these were built into the system. To create a 7-year gap, you wouldn't need a bug. You would need the code to be fundamentally laughably wrong about the very nature of our solar system. And it wasn't. The Inquest was brutal, meticulous, and ultimately fruitless. After months of relentless cross-examination of independent verification by teams in Europe, Asia, and the Americas, the verdict was in. Our instruments had not lied. Our calculations were not flawed. We had seen what we thought we had seen. The ghost was not in the machine. And with that comforting possibility extinguished, a far deeper chill began to set in. If the error wasn't at our end of the cosmic telephone line, perhaps it was on the line itself. The 168,000 light-year journey from the Large Magellanic Cloud to Earth is not a simple straight line through empty space. The universe is not a vacuum. It is a landscape sculpted by gravity. This brought the investigation to its second major suspect, a gravitational lens. It was on the face of it the most elegant and plausible natural explanation. General relativity, Einstein's masterwork, tells us that mass warps the fabric of space-time. A massive object like a galaxy cluster, or even a wandering black hole sitting between us and the supernova, could act like a cosmic telescope. Its immense gravity would bend the path of light, focusing it and magnifying it. Crucially, it could also create multiple paths for that light to travel. Imagine a river flowing around a large boulder. The water splits, travels along different sides, and rejoins on the other side. Light travelling through warped space-time can do the same. One path might be slightly shorter, or travel through a less severely curved region of space, allowing that beam of light to arrive earlier than the light taking a longer, more distorted route. We have seen this phenomenon before. The light from distant quasars can be split by an intervening galaxy, creating multiple images of the same object, whose light arrives at different times, days, weeks, or even months apart. Could an unseen lens have created a cosmic shortcut for the supernova's light, a gravitational wormhole of sorts that shaved 7 whole years off its journey time? The idea was tantalizing. It was physics we understood. It would be a phenomenal discovery, but a familiar one. It wouldn't break the universe. So the search began for the lens. Every telescope capable of peering into the deep darkness of intergalactic space was pointed at the trajectory. They scanned the foreground, hunting for the faint signature of a massive object. They looked for the telltale gravitational distortion of background galaxies, the subtle warping of their shapes that would betray the presence of a massive invisible anchor. But the space between here and there was obstinately, stubbornly empty. There was no galaxy cluster, no dwarf galaxy, not even a rogue globular cluster. The models grew more and more desperate. The theorists proposed a lens made not of stars and gas, but of pure dark matter, a silent, invisible behemoth of the one substance that makes up most of the universe's mass. Even then, the math refused to cooperate. To create a time delay of 7 years, the lensing object would need to be extraordinarily massive, and its alignment with the supernova and Earth would have to be cosmically perfect, a bullseye across 168,000 light-years. The models showed that such a massive dark matter halo, even if invisible, would have a gravitational influence. It would perturb the orbits of the small satellite galaxies that swarm our own Milky Way. It would leave footprints. Astronomers checked. They looked at the elegant dance of the Magellanic Clouds, at the faint streams of stars torn from dwarf galaxies by our own gravity. Their orbits were clean. They showed no sign of being disturbed by a hidden colossus. The lens would have to be a phantom impossibly massive yet gravitationally silent. It was a contradiction in terms. The theory collapsed under the weight of its own implausibility. There was no shortcut. There was no gravitational express lane. The light, it seemed, had travelled the standard route. It just got here inexplicably fast. The search for an explanation, now growing more urgent, turned away from the journey and towards the source itself. The star, Sanderleak, 69202. What if it was not a normal star? What if its death was a new and exotic type of stellar cataclysm, one that somehow broadcast a warning signal, an advance notice of its own demise? This was the third line of defense against the unbelievable. Perhaps the laws of stellar evolution were incomplete. We have a robust, well-tested model for how a star like this one dies. For thousands of years, its core fuses heavier and heavier elements, a titanic nuclear furnace, held in a delicate balance between the outward push of radiation and the inward crush of its own immense gravity. Eventually, the core creates iron, and with iron, the fusion stops. It is a nuclear dead end. The outward pressure vanishes in an instant, and gravity, patient and relentless, finally wins. The core collapses, catastrophically rebounding in a shockwave that obliterates the star. That is the supernova. The light from that final brilliant flash is what we see. But what if something happened before? That could the star in its final death throes have emitted some sort of precursor event? A colossal burst of neutrinos, or a jet of exotic particles that travelled faster than the light from the main explosion? The idea had a certain appeal. It felt like new physics, but localised, contained to the star itself. It wouldn't mean the speed of light was wrong everywhere, just that something else could, in these specific violent circumstances, go faster. Neutrino observatories around the world were a crucial piece of the puzzle. These strange subterranean telescopes don't look for light. They look for the universe's most elusive ghosts. Trillions of neutrinos from the supernova passed through the Earth, and a tiny handful were snagged by detectors buried deep underground in mines and under mountains. Crucially, these neutrinos were detected just a few hours before the light from the supernova arrived. This was expected. Inside the collapsing star's ultra-dense core, light is trapped, bouncing around in a particle traffic jam. Neutrinos, however, are antisocial. They barely interact with matter at all. They escape the core almost instantly, streaming out into space while the shockwave and the light are still fighting their way out. They get a few-hour head start. Not a 7-year one. The scientists looked at their neutrino data again. Was there another earlier burst? A faint tremor of neutrinos that arrived 7 years ago. A ghostly postcard from the future. They scoured the archives, and again they found nothing. The neutrino signal was textbook perfect, a single sharp spike, arriving exactly where theory predicted it should just hours before the light. The star had not sent a messenger. This forced the theorists to contort their models into even stranger shapes. Maybe the supernova happened in stages. A quiet explosion first, one that produced some kind of faster-than-light signal, but very little visible light, followed 7 years later by the main brilliant detonation. It was an idea born of pure desperation. There is absolutely no known physics that would allow for such a thing. A supernova is a one-time event. It is the end of the story. To have it happen in 2 acts separated by 7 years was like a man dying of a gunshot wound and then getting up 7 years later to die from it again, but more loudly. Furthermore, we had been watching this star for decades before it exploded. We have photographic plates from the early 20th century. We have detailed spectral readings. It was a known entity, a well-behaved blue supergiant showing no signs of any exotic, precedent-shattering physics. It was simply sitting there, burning its nuclear fuel right up until the moment it shouldn't have died. And with that, the third and final conventional door slammed shut. The error was not in our instruments. The path was not shortened by a gravitational illusion. The star did not cheat. You can feel the silence that must have descended upon the world's laboratories and universities. The quiet hum of supercomputers seemed louder. The chalk dust on old blackboards seemed to hold a heavier weight. Scientists had followed the evidence with the rigorous discipline that is the bedrock of their craft. They had tried with all their collective genius to make the problem go away. They had hoped for a simple answer, and they had failed. They were now standing at the edge of a precipice, staring into a chasm of profound ignorance. All the easy roads had led to dead ends. All the comfortable assumptions had been stripped away one by one. They were left with the raw, naked, terrifying fact. A signal bound by the universe's most sacred speed limit had arrived 7 years ahead of schedule. This was no longer an anomaly. It was a verdict, a judgment rendered on our understanding of the cosmos. And it suggested that something was fundamentally wrong. Not with the star, not with the journey, not with us, but with the very rules themselves. The questions that remained were no longer about astronomy. They were about the nature of reality. Is the speed of light truly constant, a rigid cosmic law, or is it merely a suggestion? Is the vast emptiness of space truly uniform, or does it contain hidden textures, subtle currents and eddies in the fabric of space-time that can speed a traveller along? We have always looked out into the universe and assumed that the physics we find here on our little world applies equally out there in the deepest reaches of the night. This is the cosmological principle, the foundation of everything we know. But what if it isn't true? What if somewhere out in the dark the universe plays by a different set of rules? Humanity was now confronted with a truth more unsettling than any fiction. The light from a dead star had reached across the void not just as a message but as an impossibility. And in doing so, it had thrown open a door that we never even knew existed. A door that led to a place where the familiar lines between cause and effect between now and then simply dissolved. The calculations were unyielding, the models stubbornly consistent. Every simulation we ran, every theory we applied ended in the same impasse. It was a 7-year paradox, an impossible prelude whispered across the void. The star's light, its spectral signature, identical in every way, was reaching our telescopes years before it was supposed to. It was as if a courier had broken the cosmic speed limit, a law we believed to be absolute and immutable. We had exhausted the conventional, pushing every known theory to its breaking point. Could the star itself be ejecting material at unimaginable speeds? No, the physics of such an event would have torn it apart, painting the surrounding space with a detectable, violent signature we did not see. Perhaps light itself behaved differently over such vast distances, its speed not a constant, but a variable, decaying or accelerating over time. This was a tantalizing, almost heretical idea, but it would require dismantling a century of physics, upending the very foundations upon which we build our understanding of the universe, and for what to explain a single confounding anomaly. The principle of Occam's razor, that the simplest explanation is often the best, seemed to mock us from the sidelines. There was no simple explanation. The team was adrift in a sea of failed hypotheses, the frustration palpable. The star was a ghost, its early arrival, a message we could not decipher. We were missing something fundamental, a key piece of the cosmic puzzle that was so profound, so counterintuitive, it lay just beyond our conceptual horizon. The answer, it turned out, wouldn't come from studying the star itself. It wouldn't come from a new theory of light. It would come from reimagining the very stage upon which the drama was unfolding. It would come from revisiting the work of a single mind who over 100 years ago taught us that space is not an empty passive void. It is an active dynamic entity, a fabric that can be bent, stretched and warped by the presence of mass and energy. To solve the riddle of the light arriving too soon, we had to first understand that the path it took was not a straight line. Because in the universe of Albert Einstein's, there are no straight lines. He gave us a new vision of gravity, a revolutionary upheaval of Newtonian thought. For centuries we saw gravity as a mysterious invisible force, a kind of instantaneous cosmic string pulling objects toward one another. But Einstein offered a picture of breathtaking elegance and staggering power. Gravity, he proposed, is not a force in space at all. Gravity is the shape of space, or more accurately of space-time. Imagine it not as an empty arena but as a vast taut sheet of rubber. It is the four-dimensional fabric of the cosmos. Now place a bowling ball in its centre. The fabric sags, it curves, it creates a deep well in its own geometry. This curvature, this depression in the fabric, is what we perceive as gravity. A smaller marble rolled nearby doesn't fall toward the bowling ball because of some magical pull. It simply follows the curve in the fabric, its path dictated by the geometry, created by the larger mass. It is an object moving in a straight line through a curved space. This is the essence of general relativity, a theory so profound it rewrote our entire conception of reality. The Earth is not tethered to the Sun by an invisible rope. It is rolling along the inside of a vast gravitational valley, a valley sculpted into the fabric of space-time by the Sun's immense mass. Our entire solar system is a delicate dance of celestial bodies, each following the contours and ripples of this invisible, flexible medium. Every star, every planet, every moon, every one of us is constantly navigating a landscape of gravitational peaks and troughs. But Einstein's theory made an even more audacious prediction. If mass can bend space, and if everything must travel through that space, then it stood to reason that even light, the fastest thing in the universe, must also follow these curves. Light composed of massless photons should by all Newtonian logic be immune to gravity. Yet in Einstein's universe, light has no choice. It must travel along the pathways carved into space-time. An astronaut on a spaceship shining a laser beam would perceive it as a perfectly straight line. But to a distant observer watching that beam pass by a massive star, the light would appear to bend, to deviate, to follow the gravitational contour. This wasn't just a theoretical curiosity, it was a testable prediction. And in 1919, during a total solar eclipse, the astronomer Arthur Eddington led an expedition that would change science forever. By photographing the stars near the blotted-out sun, he proved that their light was indeed being bent by the sun's gravity. Their apparent positions in the sky shifted exactly as Einstein's equations foretold. It was a triumphant confirmation the moment humanity realized that the universe was far stranger and far more elegant than we had ever imagined. This phenomenon, this bending of starlight by gravity, was given a name: gravitational lensing. And for decades it remained a fascinating but subtle effect, a celestial quirk observed only around objects like our own sun. But what if the lensing object wasn't just a star? What if it was something far, far more massive? What if the lens was an entire galaxy, a colossal metropolis of 100 billion suns, all contributing their mass to create a truly stupendous warp in space-time? Or even more, a whole cluster of galaxies, a cosmic superstructure bound together by an invisible scaffold of dark matter. The gravitational well created by such a leviathan would be immense, a chasm in the fabric of the universe itself, and the effect on the light from a distant object positioned perfectly behind it would be nothing short of spectacular. The intervening galaxy cluster becomes a lens, a natural cosmic telescope of unimaginable scale and power. It's not a lens of polished glass, of course, but a lens of pure gravity. Light from a background source, perhaps a quasar or a young galaxy, travels for billions of years across the cosmos. As it approaches the massive foreground cluster, it enters the gravitational well. The light doesn't just bend slightly, it is profoundly redirected. Space-time here is so warped, so distorted, that it acts like a celestial funhouse mirror. The light that would have missed us entirely is bent back towards our line of sight. The light that was heading directly for us is deflected elsewhere. The result is a magnificent ethereal illusion. From our vantage point on Earth, we no longer see the background object as a single point of light. Instead, its light is smeared into beautiful ghostly arcs. Sometimes, if the alignment is almost perfect, the light is warped into a complete luminous halo, known as an Einstein ring, a cosmic smoke ring encircling the lensing galaxy. In other cases, the light is split into multiple distinct points. We see 2, 3, or even 4 separate images of the exact same object, an arrangement often called an Einstein cross. It is a celestial mirage, a trick of cosmic geometry. You are seeing one star, one galaxy, but its light has been forced to take several different paths around the massive object in the middle. Imagine a large rock in the middle of a flowing river. The water must part, flowing around both sides of the rock to continue downstream. Gravitational lensing is a similar process, but in 4 dimensions. Space-time itself flows and bends around a massive object, and the light, like a boat caught in the current, is carried along these different streams. Each of these images, these ghostly twins, is the same object. They show the same spectral lines, the same temperature, the same intrinsic brightness. But they are not the same age. And this subtle but critical detail was the key that finally unlocked our paradox. This was the piece of the puzzle we had been missing. The light from these multiple images has travelled along different paths. And critically, these paths are not of equal length. Think back to the river and the rock. One side of the rock might have a clearer, more direct channel, while the other side is turbulent, forcing the water to take a more meandering route. Even if the water splits at the exact same moment, the 2 streams will not arrive at a point downstream at the same time. The same principle applies to the light of our distant, mysterious star. The team began to work with a feverish intensity, a new hypothesis galvanizing them. What if our star wasn't a freak of nature? What if its light wasn't breaking any laws? What if between us and that star there lay a massive unseen object, acting as a powerful gravitational lens, an object we couldn't detect directly, perhaps a cluster of galaxies too dim to see, or even a dense concentration of the enigmatic dark matter that we know constitutes the vast majority of mass in the universe? This invisible mass would be the cosmic rock in the river of space-time, and the light from our star, upon reaching this gravitational obstacle, would be forced to split to travel along multiple different paths to reach our telescopes. Suddenly the board was reset. The problem was no longer about a single beam of light arriving 7 years early. The problem was now about multiple beams of light, multiple images of the same star arriving at completely different times. The light we had detected, the signal that had confounded us for so long, was simply the first to arrive. It was the light that had travelled along the fastest possible route. But how can a bent, warped path be faster than a more direct one? Here lies the final elegant twist in Einstein's theory. The warping of space-time doesn't just affect distance, it affects time itself. This is known as gravitational time dilation. Clocks tick more slowly in stronger gravitational fields. A clock at sea level will run infinitesimally slower than a clock on a mountaintop. The effect is real, and it's something our GPS satellites must correct for every single day. When light from our lensed star travels, it navigates a complex landscape of space-time curvature. The different paths around the lensing mass pass through regions of slightly different gravitational intensity. One path might be geometrically longer in terms of pure distance, but it could skim through a region where space-time is less severely warped. In this region, time flows just a fraction of a second faster. Another path might be geometrically shorter, but it plunges deeper into the gravity well closer to the heart of the lensing mass. Here, space-time is more distorted and time itself is slowed down. This slowing effect is known as the Shapiro delay. The light is fighting its way out of a deeper gravitational trough, and this temporal drag adds years, decades, or even centuries to its journey. So we have 2 competing effects: the physical length of the path and the gravitational time delay experienced along that path. The light we saw first was the winner of this cosmic race. It travelled a path that offered the perfect balance, a Goldilocks route that minimised its total travel time. It was the first echo of a distant event, the herald arriving on the quickest road. The 7-year gap was no longer a paradox. It was a prediction. It was the time difference, the delay between the arrival of the light from the first path and the light from the others. The models, once unyielding and contradictory, now snapped into perfect focus. When we programmed the laws of general relativity into our simulations, when we placed a hypothetical massive lens between us and the star, the numbers worked. The confounding 7-year discrepancy transformed from an impossible violation of physics into a beautiful confirmation of it. The sense of relief, of sheer intellectual catharsis, was overwhelming. We weren't looking at a star breaking the laws of the universe. We were looking at the universe using its own laws to play a magnificent trick on us, a trick that revealed a deeper truth. The early light was not early at all. The other images were simply late. We had found our ghost. The star's impossible behaviour was the signature of a colossal invisible structure standing between us and it, its gravity so immense it could bend light and warp time. And in that moment of revelation, one mystery was solved, only to be replaced by a new one, perhaps even more profound. We had proven the existence of the cosmic lens. Now we had to answer the terrifying and exhilarating question, what is it made of, so a ghost in the machine? The outrageous 7-year temporal leap of this one distant star now had a plausible phantom culprit gravity itself. Not the familiar gravity that holds you to your chair, but a colossal universe-bending distortion of space-time, a cosmic lens of unimaginable scale. This hypothesis, elegant and terrifying in its implications, transformed the anomaly from a mere curiosity into a breadcrumb trail, a clue leading us toward one of the universe's unseen titans. But proposing a ghost and capturing it are two vastly different things. The challenge was now laid bare. It wasn't enough to say a gravitational lens was responsible. We had to find it. We had to prove it. The global astronomical community, now united in this singular breathtaking pursuit, mobilized for a search unlike any other. They were hunting for an object that by its very nature was likely invisible, an object whose only signature was the impossible arrival of a light from a star that should still be 7 years in its future. The first great battleground was here on Earth, in the silent, high-altitude deserts, where humanity's largest eyes gaze into the deep. The problem is our own planet. The very air we breathe, the precious life-giving atmosphere, is a shimmering, turbulent ocean that blurs and distorts the faint pinpricks of light from the cosmos. For a task this precise searching for impossibly faint multiple images of our time travel star, huddled close together, this atmospheric chaos is a fatal flaw. You are in effect trying to read the fine print on a coin at the bottom of a turbulent swimming pool. To overcome this, astronomers unleashed one of their most ingenious weapons, adaptive optics. It is a system of breathtaking complexity, a dance of light and silicon designed to outwit the sky itself. Imagine a powerful laser shooting up from the heart of the observatory, a brilliant synthetic star painted onto the upper atmosphere. A sensor watches this artificial beacon, measuring with furious speed thousands of times every second how the air contorts its perfect light. These measurements are fed into a supercomputer which calculates the precise inverse distortion needed to cancel out the atmospheric blur. The final act of this technological symphony happens at a mirror no larger than a dinner plate, but more perfect than any you have ever seen. This is the deformable mirror, a thin, flexible surface attached to hundreds, sometimes thousands of tiny piston-like actuators. In a silent, furious ballet, these actuators push and pull on the mirror, warping its surface in real time to create a shape that is the exact opposite of the atmospheric distortion. The result is a miracle of engineering. Starlight, having travelled for billions of years on a perfect path only to be scrambled in its final millisecond by Earth's air, is caught unscrambled and refocused into a single crystalline point. The swimming pool surface is rendered momentarily magically still. Only with this manufactured perfection could we even begin the search for the lens's telltale signature, the Einstein cross or Einstein ring, ghostly echoes of our star split, and smeared around the unseen lensing mass. Night after night, the great observatories of Chile and Hawaii stared at that one unassuming patch of sky, their adaptive optics systems working at the very limit of their capability. They were looking for phantom stars, infinitesimally faint copies of the one that had so brazenly broken the rules of time. If the lensing hypothesis was correct, the light from our star hadn't taken just one path to Earth. It had taken several. The primary image, the one that arrived 7 years early, must have travelled through the very deepest part of the lens's gravitational well, a cosmic shortcut through warped space-time. But other light rays would have been deflected on wider paths travelling slightly longer distances through weaker parts of the gravitational field. These paths would create other images fainter and arriving later. One might have arrived 3 years ago. Another might be arriving right now. A third might be due in a decade. We just had to find them. The digital sensors gathered terabytes of data, each pixel a potential clue, while algorithms scoured the images, comparing them, subtracting them, searching for any new point of light that wasn't there the night before, a celestial needle in a haystack of cosmic proportions. Yet even with this terrestrial army of telescopes, the odds were long. For the sharpest, most unambiguous view, we had to rise above the atmosphere entirely. We had to go to space. The call went out to the Hubble Space Telescope, the venerable eye in the sky that has for decades defined our vision of the cosmos. Hubble's gift is its stability and its exquisitely sharp vision across the visible and ultraviolet spectrum. Free from the blurring effects of air, it can measure the positions of celestial objects with a precision that ground-based telescopes can only dream of. Its mission was astrometry, to map the exact location of our time-travelling star and everything around it, establishing a definitive baseline. If any new images were to appear, Hubble would pinpoint their coordinates with unforgiving accuracy, allowing us to measure the geometry of the lensing effect. It would stare unblinking for hours, then days, building up an image of unparalleled depth, a portrait of this cosmic crime scene. But the true game-changer, the instrument that felt almost purpose-built for this mystery, was the James Webb Space Telescope. Webb sees the universe in infrared light, the long, stretched-out wavelengths that are invisible to our eyes and even to Hubble. This is the realm of the cool, the distant, and the obscured. If the lensing object was a swarm of dim brown dwarfs, or a galaxy veiled in thick dust, Webb could peer right through the fog and see it. More importantly, its infrared sensitivity was perfect for hunting the lensed images themselves. Light that has travelled for billions of years across the expanding universe gets stretched to a phenomenon known as redshift. The farther the light has travelled, the more its wavelength is shifted toward the red end of the spectrum. For a star as distant as ours, its light would be brightest in the infrared Webb's home turf. So while Hubble stood guard mapping the scene in visible light, Webb began a deep penetrating search, hoping to catch the faint ruddy glow of a delayed echo, a ghostly twin of our star finally completing its longer journey across the cosmos. The search for these phantom images was only one half of the equation. The other half was far more daunting, finding the lens itself. How do you find an object that emits no light? You look for its shadow. Not a shadow of darkness, but a shadow of gravity. You map its influence. This is where the true detective work began, as astronomers considered the gallery of cosmic suspects, each more exotic and unsettling than the last. The first and perhaps most dramatic possibility was a rogue black hole. Not the supermassive monsters at the centres of galaxies, but a solitary stellar mass black hole forged in the death of a massive star, and then flung out into the intergalactic void by some violent gravitational encounter. Wandering the darkness alone for eons, it would be a perfect gravitational lens, compact, massive, and utterly invisible. Finding one would be a landmark discovery, confirming theories about the chaotic dynamics of galaxy formation. But for it to create a 7-year time advance, it would have to be extraordinarily massive, many thousands of times the mass of our Sun, and our alignment with it would have to be cosmically almost impossibly precise. The chances were slim, but the universe has a habit of producing the improbable. A more likely and in many ways more profound suspect was a dark matter halo. We believe that every galaxy, including our own Milky Way, is embedded in a vast spherical cloud of this mysterious invisible substance. Dark matter is the gravitational scaffolding of the universe. Its gravity is what holds galaxies together and dictates the grand structure of the cosmos. Yet we have never directly detected it. We only know it's there by the gravitational pull it exerts on the things we can see. What if the light from our star passed directly through the dense central core of one of these halos, a halo belonging to a galaxy so far away it's too faint to see, or, stranger still, a halo that failed to form a galaxy at all? This would be an entirely different kind of lens. Not a single sharp point of gravity like a black hole, but a diffuse, sprawling, and potentially lumpy distribution of mass. Proving this would be monumental. It would be the first time we had ever used gravitational lensing to map the detailed inner structure of a dark matter halo, weighing the invisible substance that dominates the universe by watching how it bends time itself. The data from such an event would provide more insight into the nature of dark matter than decades of earthbound experiments. The time travel star would become a flashlight illuminating the very bones of the cosmos. And then there was the third and most ghostly possibility, a concept that exists on the very edge of cosmological theory, a dark galaxy. Imagine a galaxy that is a near-perfect failure. It possesses a massive dark matter halo, just like a normal galaxy, and it managed to pull in vast reservoirs of primordial gas. But for some unknown reason, the process of star formation never ignited. The gas remained cold and diffuse, never collapsing into the brilliant shining furnaces we call stars. The result would be a celestial ghost town, a full-sized galactic structure with the mass of 1 billion suns but utterly devoid of light. A dark galaxy would be almost impossible to detect by any other means. It is a presence defined only by its absence. If such an object were sitting between us and the time-travelling star, it would provide the necessary mass to create the lensing effect while remaining completely invisible to even our most powerful telescopes. Discovering a dark galaxy would not just solve the riddle of our star, it would rewrite our understanding of galaxy formation, revealing a hidden population of failed galaxies littering the cosmic voids. Each of these possibilities, the lone wanderer, the invisible scaffold, the ghost city, presented its own set of unique theoretical challenges. The greatest of these was the sheer magnitude of the time advance. 7 years. Gravitational lensing events are observed all the time, but the time delays between images are typically on the order of days, weeks, or perhaps a year or two for the most extreme cases. A delay of 7 years is an outlier of historic proportions. It implies a gravitational well of almost inconceivable depth and complexity. A simple, smooth, symmetrical lens like a perfect glass sphere couldn't produce such an effect. The mathematics demanded something more. The geometry of spacetime in the lens's vicinity had to be extraordinarily complex, a gnarled, twisted tapestry of gravitational potential. This is where the observers had to turn to the theorists. On supercomputers across the world, teams began the Herculean task of lens modelling. It is a form of cosmic reverse engineering. You take the known quantities, the position of the star, its brightness, the hypothetical positions of its lensed images, and that all-important 7-year time delay, and you ask the computer what kind of mass distribution could possibly create this reality. The computers churned through millions of virtual universes, each with a slightly different lens. They tested models with a single compact object. They tested models with a diffuse clumpy halo. They tweaked the mass, the density profile, the distance, and the alignment over and over, searching for a configuration that matched the bizarre observations. What they were building was a map of gravity, a topographical chart of a warped region of space-time billions of light-years away. Every successful simulation was another piece of circumstantial evidence, another line of code suggesting that the ghost we were hunting was real. As the data from Hubble and Webb began to trickle in, painstakingly processed and analysed, the first hints of an answer began to emerge, and they were not what anyone expected. The deep-field images from Webb did in fact reveal a potential second image of our star. It was incredibly faint, a mere handful of infrared photons captured by the telescope's massive mirror. But it was there. A ghost had been spotted. The excitement in the astronomical community was electric. This was the smoking gun. But when they measured its position and brightness, a profound sense of confusion set in. The new image was in the wrong place. According to every simple model, a single black hole, a smooth dark matter halo, this second image should have been closer to the first, and its brightness should have had a specific ratio. The observed image broke all the rules. It was too far away and far too dim. Suddenly the problem had become exponentially more complex. The elegant solution of a single massive object was crumbling. A lone black hole couldn't account for this configuration. Perfectly spherical dark matter halo couldn't do it either. The data was pointing toward a deeply unsettling conclusion. The lensing object was not a single simple thing. It was messy. It was clumpy. It was a complex system of gravitational wells, a whole cluster of unseen masses working in concert to produce the bizarre temporal and spatial distortions we were witnessing. The ghost we were hunting wasn't a solitary phantom. It appeared to be a whole graveyard. The lens itself, the very tool we were using to understand the time travel star, had now become the central mystery. We had set out to explain an impossible arrival of light, and in doing so we had stumbled upon an unseen structure in the universe whose very existence defies our neat and tidy models of the cosmos. The path to understanding had not led to a simple answer, but to a deeper, more profound, and far more disturbing question. So the gauntlet had been thrown down not by a rival, but by reality itself. The hypothesis was as elegant as it was audacious. A colossal, invisible object, a phantom of pure gravity, had stood directly between our telescopes and that dying star. This cosmic titan, a gravitational lens of almost impossible power, had supposedly warped the very fabric of space-time around it. It was a beautiful theory, a lifeline for physicists drowning in paradox. But in science, beauty is never enough. It demanded proof, a smoking gun fired across 1 billion light-years. And so the great hunt began a search not for a thing, but for a shadow. An army of astronomers, a global network of eyes, turned their instruments back to that one now empty patch of sky. They weren't looking for the star itself. Its light had faded into memory. They were searching for its ghosts. According to the equations of general relativity, a lens of this magnitude wouldn't just bend the light from the supernova, it would shatter it. It would create multiple distorted images of the same event like a celestial house of mirrors. Each image would be a faint, warped echo of the original explosion, its light having taken a slightly different path around the massive object. Think of it as a river flowing around a great smooth boulder. The water splits some streams, taking a longer winding route, others a more direct one before eventually rejoining downstream. The light from that star had done the same, and the different paths meant different travel times. The theory proposed that the bright flash we saw 7 years ahead of schedule was the light that had taken the most extreme shortcut. It was the first and fastest stream to reach us. If the theory was right, then somewhere out there in the darkness, the other streams of light, the slower echoes, were still on their way. Or perhaps they had already arrived too faint to have been noticed before. The challenge was monumental, akin to finding a single specific grain of sand on every beach on Earth all at once. These predicted images would be thousands, even millions of times fainter than the initial premature burst of light. They would be smeared and stretched by the lens's gravity into bizarre arcs and ethereal streaks. You are looking for the faintest of whispers in a cosmic roar. Weeks turned into months. Telescopes in the high deserts of Chile and the volcanic peaks of Hawaii stared relentlessly night after agonizing night. Supercomputers churned through petabytes of data, their algorithms trained to hunt for the signature of gravitationally lensed light. The community held its breath. Skepticism, once a healthy current, began to solidify into doubt. Perhaps the 7-year anomaly was something else entirely, some new and terrifying physics that we simply did not understand. The silence from the cosmos was deafening. The theory, so beautiful and so elegant, was on the verge of collapse. And then it happened. Not with a triumphant shout, but with a quiet query from a graduate student in a darkened control room in Germany. She was running a deep field analysis, stacking hundreds of long exposure images to digitally peel back the layers of the universe, searching for anything unusual. There in the data was a smudge. It was an impossibly faint, elongated crescent of light, curving gently around a point of absolute blackness. It didn't look like a galaxy. It didn't look like a nebula. It looked like a brushstroke of phantom light painted on the void. At first, it was dismissed as an artifact, a glitch in the sensor cosmic ray interference, anything but what they were hoping for. But the smudge refused to disappear. It was present in image after image, a persistent ghost in the machine. Spectroscopic analysis began immediately, a frantic effort to dissect that light to read its chemical barcode. The team worked for 72 hours straight, fueled by coffee and raw adrenaline. When the results finally came in, a hushed reverence fell over the room. The spectrum was a perfect match. The chemical signature of heavy elements, the unique fingerprint of a massive star in its final death throes, was identical to that of the supernova that had appeared 7 years too early. It was the star. They had found the first echo. They had found proof that the light had been split. The discovery sent a shockwave through the world of astrophysics. It was no longer a question of if there was a lens, but what it was. The single ghostly arc of light was a clue, a breadcrumb. The precise shape of that arc, its curvature, and its distance from the centre of the lensing effect allowed astronomers to begin to model the invisible object at its heart. The equations, once theoretical, now had real data to work with. They became a kind of gravitational sonar pinging the structure of space-time to map the unseen mass. The models predicted that if the first arc was there had to be more. At least 2 other even fainter images should exist, forming a pattern known as an Einstein cross, a cosmic crucifix with the lensing object sitting unseen at its centre. The hunt was reignited, but this time it was not a blind search. They knew exactly where to look. Using the combined power of the James Webb and Hubble space telescopes, they focused all their energy on that one minuscule patch of sky. They were pushing the instruments to the very edge of their capabilities, staring deeper into the abyss than ever before. And as the new ultra-deep field images were processed, the universe finally surrendered its secret. There they were. 2 more points of light, infinitesimally small, positioned exactly where the models of general relativity predicted they would be. A third, even more distorted smear of light was also identified, completing the celestial quartet. You could almost feel the collective exhale of the entire scientific community. Before them on the screen was a perfect 4-leaf clover of light, the spectral ghosts of a long-dead star wrapped around an unseen heart. This was the smoking gun. This was the irrefutable, unambiguous evidence that something monstrously massive was sitting in the darkness, playing games with light and time. The geometry of these 4 images became the key that unlocked the final mystery. By measuring the precise positions and distortions of each echo, scientists could now calculate the mass of the lensing object with stunning accuracy. The culprit was not a single black hole as many had suspected. It was something far rarer. The calculations pointed to a compact quiescent galaxy, a relic from the early universe. This ancient galaxy was composed almost entirely of dark matter, its few stars having burned out billions of years ago. It was a gravitational ghost town, invisible to almost every form of observation, betraying its existence only through its immense gravitational pull. This dark matter leviathan, weighing as much as 100 billion suns, had created a gravitational well so deep, so profoundly steep, that it acted as a perfect cosmic telescope. But the final piece of the puzzle, the one that would seal the case forever, was the measurement of time itself. The theory wasn't just that the light was split into 4 images, it was that each image had taken a different amount of time to reach us. The path differences weren't just spatial, they were temporal. The initial bright flash was the light that had travelled closest to the lens, whipped around by its gravity in a tight, fast arc. The other 3 images, the fainter ghosts, had taken longer routes, travelling through less severely warped regions of space. Now, with all 4 images identified, astronomers could execute a breathtaking feat. By analysing the subtle flickering patterns within the light of each image, remnants of the turbulent explosion itself, they could sync them up like matching the waveforms of 4 different audio recordings of the same event. They could directly measure the time delay between the arrival of each echo. The team worked in a state of intense, focused anticipation. They were comparing the measured time delays against the predictions derived from the 7-year anomaly that had started this whole affair. The numbers had to match. If they didn't, the entire magnificent structure of their explanation would come crashing down. The lead astrophysicist watched as the final calculations scrolled across her screen. The time delay between the first bright flash and the faintest, most distant ghostly image was calculated from the observational data. The number that appeared was 6 years, 11 months and 2 weeks. It was a perfect match. Within the margin of error, it was exactly the paradox they had started with. The mystery was solved. The 7-year leap into the future was not a violation of causality, it was a consequence of it. The light from that star had not broken the speed of light, it had simply been given a shortcut. Imagine the fabric of space-time as a vast flat elastic sheet. A star's light travels across it in a straight line. But now place a massive bowling ball, our dark matter galaxy, onto that sheet. It creates a deep curving indentation. A beam of light approaching this indentation has a choice. It can travel far around the edge of the dip, which is a long, slow path, or it can skim the very edge of the bowling ball, dipping into the indentation and climbing back out. From our perspective, looking down from above, this dipping path appears to be a much shorter distance across the sheet than the long way around. The light that arrived 7 years early was the light that took that shortcut. It dove deep into the gravitational well, riding a wave in the fabric of reality, a geodesic pathway that was physically shorter than any other route. It was an express lane through the cosmos paved by gravity itself. What we had witnessed was not time travel into the future. It was a profound optical illusion, an act of cosmic stage magic performed with the currency of space-time. The resolution of this paradox was more than just a clever answer to a riddle. It was one of the most powerful and elegant demonstrations of Einstein's theory of general relativity ever recorded. It showed us that the universe is not just the empty space between stars and galaxies. It is a dynamic, pliable medium that can be bent, stretched, and twisted by the presence of mass. It revealed that gravity is not a force that pulls, but a curvature that guides. Light, and indeed everything in the cosmos, simply follows the straightest possible path through this curved four-dimensional landscape. Sometimes, as we now knew, the straightest path isn't a straight line at all. The triumph was a testament to the relentless power of human curiosity, the drive to stare into an impossible abyss and not blink, but to ask why we had looked upon a miracle, an event that seemed to break the laws of physics, and we discovered that it was in fact the ultimate expression of them. The universe wasn't broken, our understanding of it had just become immeasurably deeper. We now know that these gravitational shortcuts exist. These cosmic superhighways carved by invisible masses are real. It forces us to ask a staggering new question. If we can receive a message from the past 7 years ahead of schedule, what other messages might be en route hurtling toward us along these hidden corridors of space-time? And what might they tell us about the future that is already on its way? And so we arrive at the end of one journey only to find ourselves at the beginning of countless others. The story of our impossible star, the phantom light that arrived 7 years ahead of schedule, has closed its first bewildering chapter. We are left not with an ending, but with a profound and resonant beginning. We have stood witness to a spectacle that defied intuition, a cosmic sleight of hand that seemed to tear up the very rulebook of the universe. For years it was an obsession, a single, maddening pixel on a detector that whispered of new physics, or more frighteningly of some fundamental error in our own understanding. We have traced its path from confounding anomaly to triumphant confirmation, a testament to the dogged persistence of the scientific spirit. You have journeyed with us through the doubts, the dead ends, and the dizzying calculations. You have seen how a team of astronomers armed with little more than mathematics and photons of ancient light stared into the abyss of the unknown and refused to blink. What they found there, what we have all now seen, was not a violation of physics, but its most glorious and extreme confirmation. This was never about a star breaking the laws of space-time. It was about a star revealing them to us in a way we had never before imagined. Albert Einstein, a man who never lived to see a single exoplanet, let alone a gravitationally lensed supernova, had once again painted a masterpiece of reality with the brushstrokes of pure thought. His elegant equations, born not from observation but from a deep intuitive search for cosmic harmony, had predicted this very magic. He told us that mass grips space-time, that the paths of light must bend to its will. But to see that principle sculpted into a phenomenon of such precision, of such temporal audacity, is to feel the intellectual foundations of the last century tremble with vindication. The arrival of that final predicted image, appearing in the sky exactly where and when the model said it would, was more than just data. It was a cosmic echo answering a question asked decades earlier, a conversation held across generations between a theorist's mind and the universe itself. The time travel star has become one of the sharpest affirmations of general relativity ever recorded. It tested the theory not in the gentle gravity of our solar system, but in the crushing labyrinthine gravitational field of a colossal galaxy cluster. This was no gentle curvature. This was a funhouse mirror of space-time warped to an almost unimaginable degree, and through it all the predictions held. The geometry of the universe as described by Einstein was not just an approximation, it was the truth rendered with breathtaking fidelity. The 7-year gap, the very feature that made the phenomenon so baffling, became the ultimate proof. It represented the physical distance travelled by light along different cosmic highways, a delay baked into the fabric of reality by the sheer weight of matter. For that prediction to come true, every component had to be right. Our understanding of gravity, our models of the intervening cluster, our calculations of the dark matter holding it all together. It was a symphony of physics, and every instrument played in perfect tune. This single event transforms our confidence in these models from academic belief into tangible, observable fact. When we now look at other distortions in the cosmos, we do so with a newfound certainty, knowing that the map Einstein gave us leads to real verifiable treasure. Yet the true legacy of this star is not simply in what it confirmed, but in what it has now empowered us to discover. It has handed us a key, a new and revolutionary instrument for prying open the universe's most stubborn secrets. This extraordinary lensing event is more than a curiosity. It is a tool. And its first and most profound application is in the hunt for the universe's missing mass dark matter. You see, the light from our distant supernova did not just pass through the stars and gas of that foreground galaxy cluster. Its path was bent primarily by a substance we cannot see, touch, or detect in any direct way. The cluster's gravitational lens is shaped not by the sprinkling of galaxies we can photograph, but by an immense invisible halo of dark matter enshrouding them. The four-leaf clover pattern of the supernova's images, the precise location of each point of light, acts as an incredibly sensitive probe mapping the gravitational landscape of that cluster. Think of it like this. If you throw a handful of marbles onto an invisible uneven surface, you can deduce the shape of that surface by where the marbles land. Here the photons from the supernova are our marbles, and the invisible surface is the dark matter halo. By measuring the distortion of the images, astronomers can reconstruct the precise distribution of mass that must be present to create such an effect. They can, in essence, weigh the ghost. They can distinguish between the mass of the visible matter, the stars, the gas, the dust, and the far greater mass of the invisible scaffold holding it all together. This single event provides one of the most detailed and robust maps of a dark matter halo ever created. It allows us to test our theories about the nature of this mysterious substance. Is it perfectly smooth, or is it clumpy on smaller scales? Does it interact with itself in subtle ways? The subtle wobbles and shifts in the lensed images, the minute variations in their brightness and position hold the answers. This star has transformed a distant galaxy cluster into a natural laboratory for fundamental physics, allowing us to study the behavior of dark matter with a precision that was previously the stuff of science fiction. We are no longer just inferring its existence, we are charting its geography. The revelations do not end there. This cosmic telescope forged by gravity itself does more than just weigh the darkness. It illuminates the faint and the far away. The same gravitational lensing that split the supernova's light into multiple images also magnified it, making it appear hundreds of times brighter than it otherwise would have. This is the universe giving us a helping hand, a natural amplifier that allows our own telescopes to peer deeper into the past than ever before. The host galaxy of the supernova, a mere smudge of light under normal circumstances, is brought into sharper focus, its details magnified by the gravitational scalpel of the foreground cluster. We can study its structure, the rate at which it's forming new stars, and even its chemical composition by analysing the magnified light. This gives us a precious detailed snapshot of a galaxy in the early universe, a glimpse into the cosmic adolescence when the universe was just a fraction of its current age. These powerful lensing events are our time machines, but they are also our microscopes. They allow us to study the building blocks of today's grand spiral and elliptical galaxies when they were still taking shape. Each time we find such a perfectly aligned system, we are granted a new window into that primordial era. We can ask questions that were once unanswerable. How quickly did the first generations of stars enrich their galaxies with heavy elements? Were early galaxies more chaotic and compact than those we see today? By collecting more of these gravitationally lensed messengers, we can begin to piece together the story of cosmic evolution, not with broad strokes, but with the fine, intricate detail of individual case studies. The time travel star has shown us the power of this technique. It has proven that with a little help from gravity, we can resolve the histories of galaxies lying at the very edge of the observable universe. It beckons us to search for more of these alignments, to build a library of the magnified past and to read the story of our own cosmic origins written in the light of these distant worlds. Perhaps most astonishingly, this celestial oracle offers us a completely new way to measure the universe itself. The 7-year time delay between the star's apparitions is more than just a cosmic curiosity, it is a cosmic ruler. We now have two crucial pieces of information: the time it took for light to travel along different paths, and from our lens models a very precise understanding of the physical difference in the length of those paths. Imagine two runners setting off on a race along two different tracks. If you know how much longer one track is than the other, and you know the time gap between their arrivals at the finish line, you can calculate their exact speed. In this cosmic analogy, the speed we are calculating is the expansion of the universe itself. This value, known as the Hubble constant, is one of the most fundamental numbers in all of cosmology. It tells us how fast our universe is growing, and by extension, it allows us to calculate its age. For decades, astronomers have been locked in a quiet but persistent crisis, a debate over the precise value of this constant. Different methods for measuring it have yielded slightly but stubbornly different answers. Measurements from the cosmic microwave background, the afterglow of the Big Bang, suggest one value. Measurements from observing supernovae in the local universe suggest another. This discrepancy, known as the Hubble tension, hints that there may be something missing from our standard model of cosmology, some new physics we have yet to uncover. Now, the time delay method championed by our time travel star provides a third completely independent way to measure the expansion. It relies on nothing but geometry and the speed of light. It is a clean, elegant technique that cuts through the systematic uncertainties that plague other methods. The value derived from this single event is a vital new piece of the puzzle. As we discover more of these time delay lenses, we will be able to refine this measurement, providing a powerful independent arbiter in one of cosmology's greatest debates. This star therefore did not just teach us about its own galaxy or the cluster in front of it. It has given us a tool to take the pulse of the entire cosmos to measure the rhythm of its unending expansion. So we are left here under the quiet canopy of our own sky, looking up with new eyes. We began with a single point of light that should not have existed, a ghost in the machine, and we have ended with a new understanding of the invisible universe, a new window into the cosmic dawn, and a new yardstick to measure all of creation. This is the profound beauty of science. It is a human endeavour driven by our insatiable curiosity that allows us to find meaning in the seemingly meaningless. The universe, it seems, is the ultimate storyteller. It does not lay out its narrative in simple prose. It speaks to us in riddles, in paradoxes, in light that arrives out of turn. It presents us with phenomena that seem at first to be impossible, a star that travels through time. A cosmic mirage. But these are not tricks meant to deceive us. They are invitations. They are challenges beckoning us to look closer, to think deeper, to refine our understanding and to push the boundaries of what we know. The universe is constantly testing our perception of it, forcing us to abandon our comfortable assumptions and embrace a reality far grander and more intricate than we could ever have conceived on our own. For every mystery we solve, we unveil a dozen more, each more profound than the last. The story of the time travel star is a powerful reminder that we're still just beginning to chart this cosmic ocean. The map is not yet complete, and there are still sea monsters in the margins, but we're no longer afraid of them. We now know that in their shadows, in the places where our theories break down, and the light behaves strangely, lies the next great leap in human knowledge. The universe will continue to surprise us, to delight us, and to humble us. And we in turn will continue to listen to its stories written in the ageless language of space-time and gravity. Our journey to that single impossible star is over, but the journey it has launched has just begun.